Picture a 5-star restaurant kitchen on a Saturday night. It's pure, unadulterated chaos. Orders are flying in, printers are chattering, chefs are yelling, pans are sizzling, waiters are weaving through a maze of bodies. Now imagine trying to coordinate all of that, not for 100 diners but for 100 million. And what if every single ingredient, every pan, every chef, and every waiter was constantly changing, disappearing, and being replaced by a new one every few seconds? The entire system would collapse into a smoldering heap of burnt food and angry customers in less than a minute. This nightmare scenario isn't just a hypothetical. It is the raw, unfiltered reality of running a modern application on the internet. Companies like Netflix, Amazon, Uber, and even the startup you just heard about, they aren't running one big simple program on a single computer. They are running thousands of tiny interconnected services spread across a global network of servers that are constantly spinning up and shutting down. When you click play on a movie, you're not just making one request. You are kicking off a frantic, high-speed ballet of dozens of microservices. One service authenticates your account. Another finds the closest server with a copy of that movie. A third service checks your subscription status. A fourth one logs your viewing data for the recommendation engine. All of this has to happen flawlessly, in the blink of an eye, for millions of people at the exact same time. So how do they do it? How do they manage this mind-bending complexity without everything crashing and burning? The answer is not an army of engineers manually flipping switches. The answer is one of the most important, yet least understood, concepts in modern technology: orchestration. And in this series, we are going to pull back the curtain and explain it so simply that you will not only understand it, you will see it everywhere. You'll understand the invisible engine that powers the digital world you live in. Forget the confusing jargon and the dense textbooks. We are going to give you the fundamental knowledge that separates the casual tech user from the person who truly understands how the modern economy functions. Whether you're a developer trying to level up, a business leader trying to make smarter tech decisions, or just a deeply curious person, this is for you. We are going to solve the problem of complexity right here, right now. To understand why orchestration is so critical, we need to take a quick trip back in time. Not that long ago, building and running software was a lot simpler. You had one big application, a monolith running on one big physical server. Think of it like a single self-sufficient food truck. The owner buys the ingredients, cooks the food, takes the orders, and handles the money. It's all in one place. Simple to manage, simple to understand. If you got more customers, you bought a bigger truck. Then things evolved. We invented something called virtualization. This allowed us to take one powerful physical server and slice it up into multiple virtual machines, or VMs. Each VM acted like its own independent computer. This was a huge leap forward. Now, our food truck owner could operate a small fleet of specialized carts from the same main truck. One cart for drinks, one for hot dogs, one for pretzels. Better efficiency, better organization. But still, you were managing a handful of distinct, relatively large units. It was manageable. Then everything changed. The entire paradigm shifted with the rise of two concepts: microservices and containers. Instead of building one giant monolithic application, companies realized it was far better to break it down into hundreds, or even thousands of tiny independent services. Each service does one specific job and does it extremely well. One microservice handles the login button. Another handles the shopping cart. A third processes credit card payments. A fourth calculates shipping costs. Think back to our food truck. This is like ditching the fleet of carts and building a massive, sprawling food court with hundreds of tiny, hyper-specialized stalls. One stall just makes the pizza dough. Another just has the sauce. A third stall only has pepperoni. Another one just runs the ovens. To make a single pizza, you need all these stalls to work together in perfect harmony. This microservice architecture is incredibly powerful. It allows different teams to work on different parts of the application independently. They can update the payment service without ever touching the shopping cart service. It allows the application to be more resilient. If the pepperoni stall runs out of pepperoni, you can still sell cheese pizzas. The whole food court doesn't shut down. But it introduces that one massive problem we started with: chaos. Absolute, overwhelming chaos. How do you deploy hundreds of these tiny services? How do you make sure they can all talk to each other? What happens if one of them crashes? And most importantly, how do you scale them? Imagine it's lunch hour on Black Friday. Suddenly, you don't need one credit card service, you need 500 of them, running instantly, to handle the flood of transactions. And an hour later, when the rush is over, you need to shut down 490 of them so you're not wasting money. Doing this manually is impossible. It is simply not humanly possible. This is the exact moment where orchestration steps onto the stage. Orchestration is the automated brain. It is the master conductor of this chaotic symphony. It's the air traffic controller for your entire application. It's the head chef who knows exactly what every single person in the kitchen should be doing at every single moment. An orchestration platform like the famous one called Kubernetes is a system designed to automatically manage the entire lifecycle of these microservices. So what does it actually do? Let's break down its core jobs. First, deployment and scheduling. You give the orchestrator your application, your collection of hundreds of little services, and you tell it how many servers you have available. The orchestrator then plays a brilliant game of high-speed Tetris. It analyzes the needs of each service, how much memory it needs, how much processing power, and it intelligently places them onto your servers in the most efficient way possible, ensuring no server is overloaded and no resources are wasted. Second, auto-scaling. This is where the magic really happens. The orchestrator constantly monitors the traffic coming into your application. Is the shopping cart service getting slammed? Before it can crash, the orchestrator automatically and instantly creates copies of that service, 10, 50, 200 of them, and distributes the traffic among them. Then, when the traffic dies down, it automatically terminates those extra copies. This is the holy grail of cloud computing. Paying for exactly what you need when you need it. It's the difference between a business surviving a massive traffic spike and collapsing under the load. Third, self-healing and resilience. In a large system, failure is not a possibility, it's a guarantee. Servers will crash. Networks will glitch. A service will stop responding. The orchestrator is a vigilant watchdog. The second it detects that a service has failed, our taco stall has caught fire, it takes action. It instantly terminates the broken one and spins up a brand new, healthy replacement on a different server, all without any human intervention. Your customer never even knows there was a problem. The system just heals itself. Fourth, service discovery and networking. With hundreds of services constantly appearing and disappearing, how does the payment service know how to find and talk to the database service? It can't have a fixed address. Its address might change every few seconds. The orchestrator handles this. It acts as a universal phone book for all the services. Any service can simply ask the orchestrator, "Hey, where can I find the login service right now?" And the orchestrator will provide the correct, up-to-the-second location. It wires everything together. And finally, effortless updates. In the old days, updating your application meant taking the entire website down for maintenance, usually in the middle of the night. With orchestration, that's ancient history. You can perform rolling updates. The orchestrator will update your services one by one. It'll spin up the new version of the service, check to make sure it's healthy and working, then route traffic to it, and only then will it shut down the old version. This process repeats across the entire fleet, resulting in zero downtime for your users. You can update your application in the middle of the day with nobody noticing a thing. So let's put it all together. Orchestration takes the impossible chaos of a modern, microservice-based application and turns it into an automated, scalable, and self-healing system. It's the reason the internet services you rely on every single day are so reliable. But what are the actual tools that do this? You've probably heard their names whispered in tech circles: Kubernetes, Docker Swarm, Amazon ECS, Google Kubernetes Engine. These are the specific platforms, the different brands of air traffic control systems that companies use. And by far, the most dominant, the undisputed king of the orchestration world, is Kubernetes. Over the rest of this series, we are going to demystify these tools completely. We'll start with the most fundamental building block of all, the container. Then we will dive deep into Kubernetes, exploring its architecture and how it actually works under the hood. We'll look at real-world examples and case studies. By the end, you'll have a rock-solid, practical understanding of this transformative technology. But before we can learn about the conductor, we have to understand the individual musicians. In cloud computing, that musician is the container. What is it? Why did it change everything? And how is it different from the virtual machines we talked about earlier? That single concept is the key that unlocks everything else. And it's exactly what we're breaking down next. To understand the container, you first have to feel the pain that created it. Imagine you're a software developer. You spend months building a beautiful, complex application on your laptop. It runs perfectly. You've tested every button, every feature. It's a masterpiece. You hand it over to the operations team to deploy it on the company's main servers. And it completely breaks. Nothing works. The operations team is frustrated, you're panicked, and everyone starts pointing fingers. You swear. But it works on my machine. This isn't just a funny meme. It was the single most frustrating, time-consuming, and expensive problem in software development for decades. Why did this happen? Because your laptop and the company's server were different environments. They had slightly different versions of the operating system, different supporting software, different configurations. It's like building a perfect engine in your garage, designed for a specific model of car, and then being shocked when it doesn't fit into a completely different car on the factory floor. The old solution to this was the virtual machine, the VM we talked about. And to understand why the container is so revolutionary, let's use an analogy. Think of a virtual machine as a single-family house. If you want to build a new house, you have to start from scratch. You buy a plot of land, that's your physical server hardware. Then you pour a concrete foundation, you run plumbing, electricity, and gas lines, that's the hypervisor and the entire guest operating system. You have to install Windows or Linux with its own kernel, its own drivers, its own background services, everything. It's a full-blown, independent operating system. Only after all of that is built can you finally put your application inside the house. This works. It absolutely solves the "it works on my machine" problem because you're not just shipping the engine. You're shipping the entire car it was built for. The house is completely isolated. The neighbor's plumbing problems won't affect yours. It's secure and self-contained. But look at the cost. Building a whole house is slow. It takes minutes to boot up that entire operating system. It's also incredibly wasteful. Every single house needs its own separate set of utilities, its own water main, its own electrical grid connection, its own sewer line. Even if the house is tiny, it needs the full infrastructure. In computing terms, each VM needs its own multi-gigabyte copy of an entire operating system, consuming huge amounts of disk space, RAM, and CPU cycles just to exist, before your application even does anything. If you need 100 applications, you need 100 separate houses, each with its own redundant infrastructure. It's like building an entire suburb when all you really needed was a place for people to live. Now imagine a different approach. Instead of a suburb of individual houses, let's build a modern apartment building. The building itself is your physical server, running one single, efficient host operating system. This building already has the massive, shared infrastructure. The foundation, the main water lines, the central electrical system. This shared infrastructure is the host operating system's kernel, the core, fundamental part of the OS that talks to the hardware. A container is like an apartment inside this building. When you want to run a new application, you don't build a whole new house. You just build out a new apartment. This apartment taps into the building's existing plumbing and electricity. It shares the host OS kernel. It doesn't need its own. But, and this is the magic, it has its own locked front door, its own walls, its own private space. Your neighbor can't see your furniture or use your kitchen. You have your own isolated environment, but you're sharing the heavy, expensive infrastructure with everyone else. This is what a container is. It's an isolated, self-contained package that holds your application, and only the essential bits it needs to run, like specific libraries and settings. It doesn't contain an entire operating system. It shares the kernel of the machine it's running on. The technology that creates these walls and locked doors in software are things called namespaces and control groups, or groups. Namespaces make the container think it has its own private operating system, its own network, its own file system, even though it's sharing the real one. Groups are like the circuit breakers and water meters for the apartment. They limit how much memory and CPU that one container can use, so it can't hog all the resources from its neighbors. So let's go back to our developer. Instead of shipping a whole house, a multi-gigabyte virtual machine, they now ship a lightweight apartment, a container that might only be a few megabytes. This container packages the application and all its specific dependencies. The exact version of the programming language, the exact libraries, the exact configuration files. It's a perfect sealed snapshot of the environment where it was proven to work. When the operations team receives this container, they don't have to install anything or worry about versions. They just run it. And because the container is a standardized, self-contained unit, it runs identically on the developer's laptop, on the company's test servers, and on the massive cloud servers for the whole world to see. The "it works on my machine" problem? Gone. Forever. This concept of containers had been around for a while in the Linux world, but it was complicated, a niche tool for experts. Then, in 2013, a company called Docker came along and changed everything. Docker didn't invent the container, but it did for containers what the Ford Model T did for the automobile. It made them accessible to everyone. Docker created a simple set of tools to build, share, and run containers. It was like getting a standardized blueprint for an apartment, a factory to build it, and a global catalog to order any prefabricated apartment you could imagine. The blueprint is a simple text file called a Docker file. The factory is the Docker engine, which reads the blueprint and builds your container automatically. And the catalog is Docker Hub, a public registry where developers can share and download millions of pre-built container images for everything from databases to web servers. Suddenly, creating these perfect, portable packages wasn't a complex engineering task. It was as easy as writing a recipe. The impact was immediate and seismic. The difference in performance is staggering. A virtual machine, that full house, can take several minutes to boot up. A container, the apartment, starts in a fraction of a second. It's the difference between building a house and just unlocking a door. The efficiency is off the charts. On a single server where you might have been able to run 10 virtual machines, you could now run hundreds or even thousands of containers, all sharing the same OS kernel, all neatly isolated from each other. This means lower cloud bills, faster development, and happier developers. It was a revolution. So now we have our perfect building block. This lightweight, fast, portable unit of software, the container. Our orchestra no longer has a few dozen massive, slow-to-move musicians. We now have thousands of tiny, agile, identical musicians. We've solved the problem of packaging and running a single application reliably. But in doing so, we've just created a brand new problem, a problem of scale. If you only have 1 or 2 apartments to manage, it's easy. But what happens when you have a skyscraper with 5,000 apartments? What happens when you have a global real estate empire with hundreds of these skyscrapers all over the world? Who decides which application, which container goes into which server? Who monitors them to make sure they're healthy? If a server goes down, who is responsible for instantly moving its hundreds of containers to a healthy server with no downtime? Who handles all the networking so they can talk to each other? Who is the building manager, the city planner, the conductor for this massive, sprawling city of containers? That, right there, is the job of the orchestrator. And the undisputed king of all orchestrators, the master conductor for the entire cloud, is a tool called Kubernetes. Kubernetes. It sounds like a complex, intimidating word, and honestly it can be. But the name itself gives us the perfect clue to understanding its power. Kubernetes is a Greek word. It means helmsman or pilot, the person steering a ship. And that's exactly what it does. It steers our entire fleet of containers through the chaotic, stormy seas of the internet. But to really understand why Kubernetes is the king, we have to go back in time. We have to go inside the one company on Earth that was dealing with container problems at a scale nobody else could even imagine: Google. Think about it. In the mid-2000s, Google was already a monster. Billions of search queries, Gmail, Google Maps, early YouTube. All of this was running on hundreds of thousands, then millions of servers spread across the globe. How on earth did they manage that? How did they update Google Search without the whole world noticing a flicker? How did they deploy new features to Gmail for millions of users simultaneously? They weren't manually logging into servers. That would be like trying to build a skyscraper with a single hammer. It's impossible. For over a decade, Google had a secret weapon, a powerful in-house system that was the stuff of legend among Silicon Valley engineers. It was called Borg. Borg was Google's internal orchestrator. It was the city planner for Google's entire global empire of applications. Every time a Google engineer wanted to launch a new service or update an old one, they didn't have to worry about finding a server with enough space. They didn't have to worry about what would happen if that server's hard drive failed. They just packaged their application into a container, handed it to Borg and told it, "Hey, I need 10 copies of this running, please. Keep them alive for me." And Borg would handle the rest. It would find the best machines to run those containers, start them up, monitor their health, and if one of them died, Borg would instantly automatically bring a new one to life on a different machine. It was the ultimate automated, self-healing system, managing millions of jobs across thousands of machines. It was the secret sauce that allowed Google to operate at a godlike scale. So, here's the billion-dollar question. If Borg was Google's secret weapon, their competitive advantage, why on earth would they give it away? In 2014, Google did something that shocked the tech world. They released an open-source project called Kubernetes, which was a redesigned version of Borg, built on all the lessons they had learned running it for over a decade. They gave their secret weapon to the world. For free. This wasn't just charity. It was one of the most brilliant business moves of the 21st century. At the time, Amazon Web Services was the undisputed giant of cloud computing. Google Cloud was a distant competitor. Google knew that the future of software was in containers, so they played the long game. They thought, what if we give everyone the best possible tool to manage containers? What if we make our internal battle-tested system the industry standard? If the whole world learns to build and manage their applications using Kubernetes, then the easiest, most powerful place to run that Kubernetes system would naturally be Google's own cloud. It was a Trojan horse. They gave away the how to make their platform the most attractive where. And it worked. Kubernetes took over the world. So what did Google actually give us? What are the fundamental ideas inside Kubernetes that came from Borg? Let's start with the absolute basics. In the Kubernetes world, we have our physical or virtual machines. These are the servers. Kubernetes calls them nodes. Think of a node as an apartment building in our city. It's a worker machine with a certain amount of CPU, memory, and storage, a certain number of floors and square footage available. Now, you might think we just put our containers directly onto the nodes. We just rent out the building. But Kubernetes adds a crucial extra layer of abstraction. It introduces a concept called a pod. A pod is the smallest, most basic unit that you can create and manage in Kubernetes. And here's the key. A pod holds one or more containers. Think of the pod as a single apartment inside the building. That apartment can have a single person living in it, a single container, which is the most common setup. But it could also have 2 or 3 people living in it. Multiple containers that are tightly coupled and need to be together. Why would you do that? Imagine you have your main web application container, but it needs a helper container that constantly pulls the latest data for it, or another one that gathers its logs. These containers need to share the same network address, like roommates sharing a Wi-Fi password, and they need to be able to access the same files, like sharing a bookshelf. By placing them in the same pod, Kubernetes guarantees they will always run on the exact same node, right next to each other. They live together, and if the pod dies, they die together. It's a brilliant way to group related processes. So we have our nodes, the apartment buildings, and we have our pods, the apartments running inside them. But who decides which apartment goes into which building? Who keeps track of all the vacancies? Who calls the repairman if a building's plumbing bursts? That is the job of the control plane. The control plane is the city hall of our Kubernetes city. It's the brain of the entire operation. It doesn't run any of your actual application containers. Instead, it's a set of processes that manage the whole system. It watches over all the nodes, keeps track of all the pods, and makes all the decisions. And this is where we get to the absolute core magic of Kubernetes, the central philosophy that makes it so powerful. It's a concept called desired state reconciliation. It sounds complicated, but the idea is beautifully simple. With Kubernetes, you, the developer, almost never command it to do things. You don't say, Kubernetes, go create a pod on node number 3. That's the old way of thinking, the manual way. Instead, you simply declare the state you want the world to be in. You write a configuration file, basically a manifest, a blueprint, and you tell the control plane, here is what I want reality to look like. I desire to have 3 identical copies of my web server pod running at all times, using this specific container image. You hand that blueprint to the control plane, and from that moment on, the control plane's only job is to work tirelessly 24/7 to make the actual state of the system match your desired state. It's a constant loop. It checks. What's the desired state? 3 web server pods. Now what's the current actual state? Counts them. Oh, I only see 2. The loop finds a difference. So it takes action. It finds a node with available space and schedules a new pod to be created there. A few seconds later, it checks again. Desired 3. Actual 3. The states match. All is well. It continues watching. Now imagine a server in your data center suddenly overheats and dies. The node goes offline and the pod that was running on it is gone. What happens? Chaos? Panic? Nope. The control plane on its next check just seconds later sees the mismatch. Desired state 3 pods. Actual state only 2. It immediately springs into action. It recognizes that the dead node is gone, marks it as unhealthy, and just like Borg did at Google, it finds a new, healthy node and creates a replacement pod there to bring the count back up to 3. This is self-healing. This is automation at its finest. You didn't have to wake up in the middle of the night. You didn't even get an alert. Kubernetes just fixed it. It treated that server failure like a minor inconvenience, not a catastrophe. You told it your destination, and the helmsman is now steering the ship, automatically correcting the course for any storm it encounters. This is the fundamental promise of orchestration. We've moved from managing individual servers to simply declaring our intent and letting a powerful, resilient system handle the messy reality of making it happen. We've built our self-healing city of apartments. But now a new problem emerges. These pods are like nomads. They can be destroyed and recreated on entirely new machines at any moment. Their internal addresses change. So, how does anyone find them? How does a user clicking a link on their phone in Ohio find their way to one of these three identical, but constantly shifting web server pods living somewhere in our massive digital city? How do the pods talk to each other? We need roads. We need a postal service. We need a smart GPS system for our city. And this is where the genius of our orchestrator, our digital city planner, truly begins to shine. Because in a city where buildings can vanish and reappear in a different location in the blink of an eye, a traditional address book is completely useless. You can't just tell a user to go to server 172 at 16.4.8, because a second later that server might be gone, replaced by 172 at 16.9.22. It's chaos. It's like trying to mail a package to a friend who moves to a new apartment every 5 minutes. The package would never arrive. So our city planner doesn't use addresses. It uses a concept far more powerful, an abstract identity. It creates something called a service. Think of a service as a permanent, unchanging post office box for a specific type of business. Let's say our 3 web server pods are all part of the web server franchise. Instead of trying to track the physical street address of each individual franchise location, we just create a single permanent PO box called Main Web Server Service. Now, any other part of our application or any user from the outside world doesn't need to know about the individual pods. They don't care if there are 3 of them or 10, or if they're all being replaced. All they need to know is the address of that one single reliable PO box, Main Web Server Service. They send their request, their data packet, to this service. And here's the magic. The service acts as a smart, tireless postal worker. It has a constantly updated list of every healthy, active web server franchise location at that exact moment. When your request arrives at the PO box, the service instantly looks at its list, picks one of the available web server pods, and forwards your request to it. This process is called load balancing. The service is distributing the incoming mail, the user traffic, evenly across all the available buildings, ensuring no single pod gets overwhelmed. If one pod is busy handling a request, the service sends the next one to a different pod. It's the ultimate traffic manager. But it gets even better. What happens if one of our web server pods crashes? In our city analogy, what if one of the franchise buildings has a fire and has to close temporarily? The orchestrator, our city planner, sees this immediately. It marks that pod as unhealthy. The main web server service, our smart postal worker, gets an instant notification. It crosses that building's address off its active delivery list. From that moment on, until the pod is repaired and comes back online, 0 traffic will be sent to it. The user on the outside never notices a thing. Their request is just seamlessly routed to one of the other 2 healthy pods. This is the foundation of self-healing systems. The network itself is intelligent. It routes around failure automatically. Okay, so that explains how different parts of our application inside the city can find each other using these stable service addresses. The user authentication pod can reliably send a message to the database pod, because they both have a permanent PO box address. But what about the rest of the world? How does a user, sitting at their laptop in Ohio, send a request that finds its way into our specific digital city and gets to the correct PO box? Our city can't just have a million PO boxes open to the entire internet. That would be a security nightmare and incredibly inefficient. Our city needs a front door. A single, heavily guarded, well-managed main gate. In the world of orchestration, this is called an ingress. Think of the ingress as the city's grand central station or international airport. It is the only official entry point for all traffic coming from the outside world. When you type urap.com into your browser, your request travels across the internet and arrives at the front door, the ingress. At this front door stands a very, very smart traffic cop called an ingress controller. This controller is the master of ceremonies. It inspects every single incoming request. It looks at the URL, the address the user is trying to reach. If the request is for urap.com/login, the ingress controller says, a login request. I know exactly where that goes. It then directs the traffic internally to the user authentication service. If the next request is for urap.com/products, the controller says, a product search. Got it. And forwards that request to the product catalog service. The ingress acts as a reverse proxy, a sophisticated switchboard for our entire city. It allows us to run dozens or even hundreds of different services, all behind a single public-facing IP address. It's what lets a single website like Amazon route you to book searches, video streaming, or your shopping cart, all of which are likely completely separate applications running in their own pods, but they all appear to live at Amazon.com. The ingress is the director, pointing the traffic to the right stage. So now we have our roads. The services are the local streets and GPS that allow pods to find each other. And the ingress is the main highway interchange connecting our city to the global internet. But in a truly modern high-security city, you need more than just roads. You need a higher level of infrastructure. You need traffic monitoring, encrypted tunnels, and automated security checkpoints. This brings us to one of the most powerful and initially confusing concepts in modern cloud computing: the service mesh. If the services and ingress are the roads on the map, the service mesh is a hyper-advanced, invisible layer of technology that is built into the roads themselves. It's like upgrading all our city streets to smart highways. Here's how it works. Our city planner, the orchestrator, decides to install a service mesh. What it does is automatically place a tiny, ultra-efficient little proxy, a sort of mini traffic cop, right next to every single pod in our city. This is called a sidecar proxy. So now our web server pod has a little sidecar buddy, and our database pod has one too. From this point on, the pods themselves no longer talk directly to each other. When the web server pod wants to send a message to the database pod, it doesn't just shout across the street. It hands the message to its little sidecar buddy. That sidecar then encrypts the message, putting it in a secure, armored van, and sends it to the database pod's sidecar buddy. The receiving sidecar decrypts the message and hands it to the database pod. The two pods think they're just talking normally, but the service mesh has created a secure, encrypted communication channel between them completely automatically. We didn't have to write a single line of code in our application to handle this encryption. The city's infrastructure now provides it for free. But security is just the beginning. This mesh of sidecar proxies sees everything. It's like having a traffic camera and a speed sensor on every single block of our city. It records every single request that flows between every single pod. This gives us a superpower called observability. We can now ask incredible questions. How many requests per second are flowing from the web servers to the database? What's the average response time? Are there any errors? Which service is running slow and causing a traffic jam for everyone else? Before the service mesh, answering these questions was a nightmare. It was like trying to diagnose a citywide traffic jam by just standing on one street corner. Now with the mesh, we have a god's eye view of the entire city's traffic flow in real time. We can see bottlenecks, pinpoint failures, and understand how all the different parts of our complex application are interacting. And it does even more. The service mesh can control traffic in incredibly sophisticated ways. Let's say we've built a new version of our web server, version 2. We're nervous about releasing it to all our users at once. With the service mesh, we can create a rule. Send 99% of the traffic to the old stable version 1, but siphon off just 1% of real user traffic and send it to the new version 2. We can then watch our new version under a small amount of real-world load, check our dashboards for errors, and gain confidence before rolling it out to everyone. This is called a canary release, and it is a cornerstone of modern, safe software deployment. So let's zoom out. Our orchestrator isn't just a construction foreman plopping down buildings. It's a master city planner, building a sophisticated, resilient, and intelligent metropolis. It uses deployments to create blueprints for our buildings, the pods. It uses services to give those buildings a permanent address and a smart local mailman, so they can talk to each other reliably. It uses an ingress to build a grand central station, the single front door to our city from the outside world. And it can use a service mesh to upgrade the very fabric of the city's roads, adding deep security, incredible observability, and granular traffic control. Our city is running. It's serving traffic. It's healing itself from failures. The network is alive and intelligent. But there's a critical piece of the puzzle we haven't touched yet. What happens when 1,000 users suddenly become 1 million? When rush hour hits our digital city, how does it respond? 3 web servers suddenly aren't enough. The roads are getting clogged. Requests are slowing down. Our users are getting frustrated. Our city doesn't just need to be resilient. It needs to be elastic. It needs to be able to grow and shrink on demand, automatically, without any human intervention. Who is watching the traffic levels? And who has the authority to decide when it's time to build 10 new web server buildings right now? The answer, the who, isn't a person. It's not a frantic manager in a control room, or a team of engineers chugging coffee and staring at graphs. The watcher, the decision maker, the one with the authority to build a data center's worth of computing power in the blink of an eye, is a system. It's a concept. It's the digital maestro of our entire cloud symphony. This is the heart of orchestration. Imagine a world-class symphony orchestra. You have hundreds of musicians. The violin section, the cellos, the trumpets, the percussion. Each one is a master of their instrument. But if you just put them all in a room and tell them to play, you get chaos. You get noise. You don't get a symphony. What's missing? The conductor. The maestro. The one person who doesn't play a single instrument, but without whom there is no music. The maestro stands at the front, holding the sheet music, the master plan. They cue the violins to come in softly, signal the trumpets for a dramatic fanfare, and control the tempo and dynamics of the entire performance, turning 100 separate noises into one glorious, unified masterpiece. In cloud computing, that maestro is the orchestrator. And the musicians? They are our resources. The web servers are the string section, handling the main melody of user requests. The databases are the powerful brass section, providing the deep, foundational data. The networking components like firewalls and load balancers are the percussion, keeping the rhythm and directing the flow. Each piece is a complex, powerful component, but left to their own devices, they're just a collection of disconnected services. The orchestrator is what turns this collection into a cohesive, functioning application. It's the brain, the central nervous system, that coordinates every single part to work in perfect harmony. But how does the maestro know what music to play? It can't just make it up. It needs the sheet music. In the world of the cloud, our sheet music is something called infrastructure as code. Now, don't let the word code scare you. Think of it less like complex programming and more like writing a fantastically detailed recipe. If you wanted to bake a cake, you wouldn't just walk into the kitchen and start throwing flour and eggs around. You'd follow a recipe. The recipe lists every ingredient, every measurement, and every step in the correct order. Preheat the oven to 350 degrees. Mix flour and sugar. Add eggs one at a time. Infrastructure as code is that recipe for our entire application environment. Instead of a human logging into a cloud provider's website and manually clicking buttons, create a server. Now choose the memory. Now set up a network. Now install the database software. We write it all down in a file. A simple text file. This file declares everything we need. It says, I need 10 web servers of this specific size. They need to be running this operating system. They need to be connected to this database, which should be this powerful. And all of them need to be behind this specific firewall with these specific rules. We hand this recipe file to our orchestrator. The orchestrator reads it and, like a master chef robot, executes it perfectly every single time. It builds the servers, configures the networks, installs the software, and connects everything together precisely as we described. The beauty of this is that it's repeatable and reliable. If we need to build the exact same environment again for testing, or for a new region, we just give the orchestrator the same recipe. No human error, no forgotten steps. Just a perfect copy every single time. This recipe, the sheet music, is the single source of truth for what our application should look like. Now, the orchestrator's job, its grand performance, can really be broken down into 3 main acts. First is provisioning. This is the act of creation. It's the conductor stepping onto the podium, tapping the baton, and bringing the entire orchestra to life from silence. The orchestrator reads our infrastructure as code file and builds everything from scratch. It calls out to the cloud provider, Amazon, Google, Microsoft, and says, give me 20 virtual servers, 3 databases, and a load balancer, and connect them like this. It lays the entire foundation. It literally provisions the resources, bringing them into existence. The second act is configuration management. This is about keeping the orchestra in tune. It's not enough to just have all the musicians on stage. Their instruments need to be perfectly tuned throughout the entire performance. In the cloud, servers can drift. A security patch might be applied to one server but missed on another. A developer trying to fix a bug at 3 a.m. might manually change a setting. This creates inconsistencies, which lead to bugs and security holes. The orchestrator acts as the ultimate enforcer of harmony. It constantly checks every single server and component against the master sheet music, our code file. If it finds a server that's out of tune, a setting that's been changed, a piece of software that's missing, it automatically fixes it. It brings it back into the desired state. It ensures that our entire environment remains exactly as we defined it, preventing that slow, dangerous drift into chaos. And that brings us to the third and most magical act, automation and scaling. This is where the maestro truly shows their genius, reacting to the audience in real time. This is the direct answer to our problem of elasticity. Our sheet music, our recipe, doesn't just describe the initial setup. It also contains the rules of engagement for when things get crazy. We write rules like, "Dear Maestro, please watch the web servers." If the average workload across the string section goes above 80% for more than 5 minutes, that means a huge crowd is loving our performance. At that point, automatically bring in 10 more violinists from backstage, get their instruments tuned, and have them join the section to handle the load. And the reverse is just as important. If the workload drops below 20% for 15 minutes, it means the crowd is thinning out. Gently dismiss half of the violinists. We don't need to pay for them to just sit there. The orchestrator does this automatically. It is constantly watching the traffic, the performance, the health of our application. When that Black Friday sale hits, the orchestrator doesn't panic. It doesn't need a human to tell it what to do. It sees the incoming wave of traffic, consults the rules we gave it, and begins provisioning and configuring new servers before the first one even gets overloaded. It seamlessly adds them to the system, spreading the traffic load perfectly. To the user, it just works. The website stays fast and responsive. And when the sale is over and the traffic vanishes, the orchestrator gracefully removes those extra servers, shrinking our infrastructure and our bill, all while we sleep. This is the promise and the power of orchestration. It's not just about building things, it's about creating a living, breathing system. A system that can build itself, heal itself, and grow or shrink in response to the real world, all guided by a plan that we've laid out. It takes the complex, chaotic world of cloud resources and conducts them into a single, resilient, and efficient symphony. But this maestro, this conductor, it isn't a single entity. It's a battlefield of ideas, a clash of titans with names you've probably heard whispered in tech circles. Kubernetes, Terraform, Ansible. Each one is a genius, but each one conducts the orchestra in a radically different way. They have different philosophies, different strengths, and different rulebooks for creating their masterpiece. So, which maestro do you choose for your application? That's where the real strategy begins. Let's start with the two heavyweights in the concert hall, Kubernetes and Docker Swarm. Think of them as two world-renowned conductors with fundamentally different approaches to music. On one side, you have the grand, classical maestro, demanding perfection and capable of conducting a 1,000-piece orchestra. On the other, you have the innovative, agile jazz ensemble leader, focused on speed, simplicity, and improvisation. First, let's talk about Kubernetes. If orchestration were an Olympic sport, Kubernetes would be the reigning decathlon champion. It's powerful, it's versatile, and frankly, it can be intimidatingly complex. Originally born inside Google to manage their own colossal applications, Kubernetes was designed to handle scale that most companies can only dream of. Its philosophy is built on a concept called declarative configuration. Now, what does that mean? Let's go back to our orchestra. With a declarative approach, you don't walk up to the conductor and say, "Tell the first violin to play a G, then have the cellos come in, then cue the timpani." That's an imperative, step-by-step command. No, with Kubernetes, you hand the conductor the entire, finished musical score for a Beethoven symphony and you say one thing: make the performance sound exactly like this. You have declared the final state you want. It is now the conductor's job to figure everything out. Who plays what, when they play it, what happens if a violinist's string breaks mid-performance, or if the entire brass section suddenly gets sick and needs to be replaced. The conductor, our Kubernetes maestro, handles all of it. It constantly compares the reality of the performance to the perfect score you gave it, and it works tirelessly to close that gap. This score in the Kubernetes world is typically a set of files written in a language called YAML. These files describe everything, every container, every network rule, every storage requirement. It's your application symphony written down on paper. And this is where Kubernetes gets its incredible power. Let's look at the musicians. In Kubernetes, a single container is rarely the star. Instead, it uses a concept called a pod. A pod is the smallest unit you can deploy. Think of it not as a single musician, but as a small, tightly knit chamber group like a string quartet. These containers inside a pod are always scheduled together, they live and die together on the same machine or node, and they can easily talk to each other as if they were in the same room. They share resources like a music stand or a microphone. This allows you to group related services together in a logical, efficient way. The conductor, the brain of the operation, is called the control plane. It's the maestro on the podium, watching over the entire orchestra of worker nodes. The servers where your pods actually run. If a node goes down, if a section of the stage collapses, the control plane sees it instantly. It consults the musical score and says, "Aha, I'm missing a string quartet and a woodwind quintet." It then automatically finds a new, stable part of the stage and recreates those pods from scratch, ensuring the symphony never stops. This is self-healing, and it's one of the platform's superpowers. But with this immense power comes immense complexity. Learning to write that perfect musical score, the YAML files, is a steep learning curve. It's like learning musical notation, theory, and composition all at once. For a small 3-piece band, this might be total overkill. You don't need a full symphonic score to play a simple blues riff. And that brings us to our other conductor, Docker Swarm. If Kubernetes is the classical maestro in a tuxedo, Docker Swarm is the cool, collected jazz bandleader in a turtleneck. Swarm's entire philosophy is the polar opposite of Kubernetes: simplicity and ease of use. It's built directly into Docker, the tool that most developers are already using to create their containers. There's almost no extra software to install or complex new concepts to learn. If you know how to use Docker, you're about 90% of the way to using Swarm. Swarm takes a more direct, imperative-like approach. It's less like handing over a full symphony and more like telling the bandleader, "I need a bass player, a drummer, and a saxophonist. Make sure there are always 3 of them on stage, and if the sax player leaves, find another one." The commands are simpler, more intuitive, and easier to get started with. You can get a cluster up and running in minutes, not days. In Swarm, the core concept is a service. You define a service like your website's front end or a database, and you tell Swarm how many replicas or copies of that service you want to run. Swarm, the bandleader, takes care of the rest. It distributes these container musicians across the available nodes, which are just servers designated as either managers or workers. The manager is the bandleader, and the workers are the band members who take direction. The beauty of Swarm is its seamless integration. It uses the standard Docker command line interface. The networking is straightforward. For a small to medium-sized application, or for a development team that wants to focus on building features rather than managing infrastructure, Swarm can feel like a breath of fresh air. It's orchestration without the headache. It's the fast, nimble, and highly effective jazz trio. So which one do you choose? This isn't a question of which is better. It's a question of which tool is right for the job. It's a strategic trade-off. You choose Kubernetes, the grand maestro, when you are building a massive, complex system that needs to be incredibly resilient and scalable. You're building an application for the next decade. You have a dedicated team of engineers, or you're willing to invest the time to master its complexity because you need its power. You need fine-grained control over every single aspect of your application, from custom network policies to advanced storage configurations. You're building the next Netflix, the next Spotify, the next global enterprise platform. You choose Docker Swarm, the agile bandleader, when your priority is speed and simplicity. You're a startup or a smaller team. You want to get your application orchestrated and running today. Your application is complex, but not globally massive internet-scale complex. You value developer productivity and want a gentle learning curve. You love the Docker ecosystem and want a tool that feels like a natural extension of it, not a whole new universe to learn. But wait, are these the only 2 conductors in town? Not at all. There are other, more specialized maestros. Consider a third option, HashiCorp Nomad. Nomad is the avant-garde conductor. Its unique strength is its flexibility. While Kubernetes and Swarm are laser-focused on conducting containers, Nomad is a general-purpose orchestrator. It can conduct anything. It can manage your Docker containers, sure, but it can also manage traditional applications, virtual machines, and even simple executable files. Nomad is the conductor who can lead an orchestra that includes a string quartet, a rock band, and a DJ, all at the same time, and make it sound coherent. It's incredibly lightweight and simple to operate, often seen as a middle ground between the simplicity of Swarm and the power of Kubernetes, but with a much broader scope. It's a powerful choice for organizations that have a mix of old and new applications and want a single tool to manage them all. Choosing your orchestrator is one of the most critical architectural decisions you'll make. It defines how your application will scale, how it will heal itself from failure, and how your team will interact with it every single day. It's the choice between the grand, powerful, and complex symphony, the fast, simple, and agile jazz trio, or the flexible, all-encompassing experimental ensemble. But no matter which maestro you choose, they all need one thing to function: a score. A detailed set of instructions that tells them exactly what masterpiece to create, which musicians to hire, and how the performance should run from start to finish. And that's where we dive into the sheet music of the cloud, the configuration files that bring these automated orchestras to life. These configuration files are the very heart of modern orchestration, and they're based on a revolutionary idea called infrastructure as code. Now, that sounds technical, but the concept is beautifully simple. Instead of clicking around in a web browser to manually set up servers, databases, and networks, you write down exactly what you want in a simple text file. Just like a composer writes down every note on sheet music, you write down every component of your digital infrastructure. You are literally writing your infrastructure into existence. Let's make this real. The most famous tool for this is called Terraform. Think of Terraform as the master architect for our orchestra. It reads our blueprint, our sheet music, and then works with the cloud providers like Amazon, Google, or Microsoft to build the entire concert hall exactly to our specifications. So what does this blueprint look like? Is it some arcane, complex programming language? Absolutely not. It's designed to be human-readable. Imagine we want to launch a website. We need a few basic things: a server to run the website's code, a database to store user information, and a network to let them talk to each other securely. In a Terraform file, you'd write a few simple blocks of text. The first block might say something like, resource, one AWS server. Let's use a small one, call it main web server, and make sure it's running the latest version of Linux. The next block would say, resource, one AWS database. A small one is fine for now. Let's call it customer database and set a password for it. And a final block might say, networking rule, allow the main web server to talk to the customer database. But, and this is critical, do not allow anyone from the public internet to access the database directly. You save this file. It's maybe 30 or 40 lines of text. Then you run one simple command in your terminal, Terraform apply. And this is where the magic happens. Terraform reads your file like an architect studying a blueprint. It connects to your cloud account and says, okay, the plan calls for one server, one database, and a security rule. It then meticulously sends the exact right commands to the cloud provider to create those resources. It waits for the server to be ready, then it creates the database, and finally it configures the network so they can communicate. In a matter of minutes, a complete, perfectly configured environment springs to life, built exactly as you described it. The power here is almost hard to overstate. First, it's repeatable. If you need to create an identical environment for testing, you just run the same file again. Bam! Perfect clone. Second, it's documented. Your infrastructure isn't a mystery anymore. It's all written down in a file that anyone on your team can read and understand. Third, and most importantly, it's version controlled. You can track changes to your infrastructure the same way a writer tracks changes to a novel. You can see who decided to upgrade the server when they did it and why. If a change causes a problem, you can instantly revert to the previous version, and Terraform will automatically put everything back the way it was. Imagine our concert hall burns down. With the old way, you'd be scrambling trying to remember how everything was built. With infrastructure as code, you just hand the original blueprint to the cloud provider and say, build it again. An identical hall is ready in minutes. So Terraform has built our stage, hired our musicians, the servers, the databases, and arranged them perfectly. The orchestra is ready. But what symphony are they going to play? Building the infrastructure is only half the story. Now we need to manage the actual application, the code that runs on that infrastructure. This is where our second piece of sheet music comes in. And it's orchestrated by a different conductor, arguably the most famous conductor in the entire cloud computing world, Kubernetes. If Terraform is the architect who builds the concert hall, Kubernetes is the world-class conductor who manages the performance itself. It doesn't worry about building the servers. It assumes the stage is already there. Its entire job is to make sure the application, the music, is performed flawlessly 24/7. Kubernetes works with something called containers. We touched on this before, but let's refresh. A container is a neat, tidy package that holds a piece of your application and everything it needs to run. Think of each container as a single, highly professional musician. They arrive with their own instrument, their own sheet music, and their own chair. They are completely self-contained and ready to play. Our job is to write the musical score for Kubernetes, telling it how we want these musicians to perform our application's symphony. This score is typically written in a format called YAML. And just like Terraform's language, YAML is designed to be stunningly simple and readable. It's basically a structured list of instructions. A Kubernetes YAML file might say, "Okay, conductor Kubernetes, for this performance, I need a new deployment. Let's call it Frontenwa." Then you specify the details. For this app, I need you to use the musician, the container, named My Awesome App, version 2. And then comes the truly mind-blowing part. You add one line. Replicas 3. What does that mean? You are telling the conductor, I want 3 instances of my web app running at all times. Not 2, not 4. Exactly 3. Kubernetes sees this instruction and immediately deploys 3 identical containers, 3 musicians, all playing the same part of the symphony. It spreads them out across the servers that Terraform built for us, ensuring they aren't all in one place. Now let's say a server has a hardware failure and one of your containers suddenly crashes. The musician has fainted on stage. In the old world, this would be a disaster. Your website would be partially down. An alarm would go off at 3 a.m., waking up an engineer who has to frantically log in and fix it. But with Kubernetes, the conductor doesn't even flinch. It has a constant watch over the orchestra. It instantly notices, hey, I was told to have 3 musicians playing this part, but I only count 2. Without any human intervention, it immediately finds a healthy server and deploys a brand new, perfect copy of that container. Within seconds, the 3rd musician is back on stage, and the symphony continues without the audience ever noticing a single missed note. This is called self-healing, and it is a cornerstone of modern orchestration. You are no longer managing individual servers, you are declaring a desired state. You tell Kubernetes, this is what I want the world to look like. And Kubernetes works tirelessly 24/7 to make it so. Want to update your website to a new version? You don't log into servers one by one. You simply edit that one line in your YAML file, changing version 2 to version 3, and hand the new sheet music to Kubernetes. The conductor then performs a graceful rolling update. It brings up a new version 3 musician, waits for them to be ready, then gently tells one of the version 2 musicians to take a break. It repeats this process, new one in, old one out, until the entire orchestra is seamlessly playing the new version of the symphony, all with zero downtime for the audience. So you see how these 2 layers work together in perfect harmony. Terraform is the macro orchestrator. It uses infrastructure as code to build the entire stage, the servers, the networks, the fundamental building blocks. It creates the perfect environment. Then Kubernetes is the micro orchestrator. It takes over that stage and uses its own configuration files, its YAML sheet music, to manage the application itself, ensuring it runs, scales, and heals automatically. This 2-part score, the Terraform blueprint for the Hall and the Kubernetes YAML for the Symphony, represents the pinnacle of automation. It allows companies to define their entire, complex, global-scale applications in a set of text files. It turns the chaotic, manual art of managing infrastructure into a predictable, repeatable, and reliable science. We've defined the infrastructure as code. We've defined the application's runtime as code. Everything is automated. Everything is self-healing. So what could possibly go wrong? What happens when our carefully composed symphony, designed for an audience of 1,000, suddenly has 100,000 people show up at the doors? How does our orchestra handle a sudden massive surge in demand without collapsing under the pressure? That ability to grow and shrink on demand is the final, crucial piece of the orchestration puzzle. And it's where the true power of the cloud is finally unleashed. This ability to dynamically adapt, to breathe with the rhythm of demand, is called elasticity. And it's not just about getting bigger. It's also about getting smaller. Because in the world of cloud computing, you pay for what you use. Every server, every slice of computing power, every gigabyte of memory has a cost associated with it, ticking away second by second. An orchestra that's playing for a stadium-sized audience when only 10 people are in the seats isn't just inefficient, it's financially ruinous. So, how does orchestration solve this? Let's step back to the pre-orchestration world for a moment. Imagine you're running a popular e-commerce website. It's the night before Black Friday. You know a tidal wave of traffic is coming. What do? You over-provision. You buy or rent a massive fleet of servers, far more than you need for a normal day just to handle that one peak. You spend weeks setting them up, configuring them, and praying you got the number right. If you aim too low, your site crashes at the moment of maximum profit, a catastrophic failure. If you aim too high, you've just wasted a colossal amount of money on hardware that will sit idle for the other 364 days of the year. And what about unexpected surges? A celebrity tweets a link to your product. Suddenly, traffic explodes by 10,000%. In the old world, a pager goes off at 3 a.m. A bleary-eyed system administrator stumbles to their laptop, frantically trying to manually launch new servers, copy the application code, configure the network, and add them to the load balancer. It's a slow, manual, error-prone process, all happening while customers are seeing error pages and your company is losing money and reputation with every passing second. This is the definition of a system that cannot scale. Orchestration changes the entire game. It replaces that panicked 3 a.m. scramble with calm, automated, intelligent precision. Let's go back to our conductor. The conductor isn't just watching the musicians. They're also listening to the audience, the demand. In the tech world, these audience reactions are called metrics. Metrics are the lifeblood of automated scaling. They are the signals that tell the orchestrator how hard the system is working. The most common metric is CPU utilization. Think of it as how much effort each musician is putting into playing their instrument. Are they casually playing, or are they red-faced and straining? Other metrics could be memory usage, the number of requests coming in per second, or the length of a queue waiting to be processed. The orchestrator, our conductor, is constantly watching these metrics. But it doesn't just watch. It acts based on a set of rules we define in advance. These rules are called an auto-scaling policy. This policy is like a special instruction written directly into the conductor's score. It might say, if the average effort, the CPU utilization, of all my violinists goes above 75% for more than 5 minutes, I need more violinists. Immediately. This is the trigger. The second part of the rule says what to do. When triggered, bring 2 new violinists from the green room, give them a copy of the sheet music, and have them join the performance. The desired number of violinists should now be 12 instead of 10. This is the scaling up action. So Black Friday traffic starts to hit. The first few users arrive and the existing servers, our 10 violinists, handle it just fine. Their CPU usage might go from 10% to 30%. No problem. But then the wave crests. Thousands of requests pour in every second. The CPU on our servers climbs 50%, 60%, 70%. And then it crosses the 75% threshold. The orchestrator sees this. It waits for 5 minutes just to make sure it's a sustained surge and not a random blip. The condition is met. The auto-scaling policy kicks in. The orchestrator automatically contacts the cloud provider, the venue manager, and says, I need 2 more virtual servers of this exact type, with this operating system. The cloud provider provisions them in seconds. The orchestrator then deploys your application onto them, configures the networking, runs all the health checks, and seamlessly adds them to the group of servers handling traffic. To the outside user, there is no interruption. The website doesn't slow down. It doesn't crash. The only thing that happens is that the capacity to handle their requests magically appeared right when it was needed. The performance swelled to meet the size of the audience flawlessly. This is known as horizontal scaling or scaling out. We're not making our existing servers more powerful. We're simply adding more of them. It's like opening more checkout lanes at a grocery store instead of trying to make one cashier scan items 3 times as fast. Horizontal scaling is the cornerstone of modern cloud architecture because it provides incredible resilience. If one of your 20 servers fails, the orchestrator simply terminates it and spins up a new one to replace it. The other 19 barely notice. There is another type called vertical scaling or scaling up. This would be like giving your one cashier a superpowered scanner. In server terms, it means adding more CPU or RAM to an existing machine. While useful in some cases, it has limits. You can only make one server so big, and if that one giant server fails, your entire application goes down with it. Orchestration platforms heavily favor the horizontal, more lanes approach. Now, what happens when the Black Friday sale is over? The traffic dies down. The requests slow to a trickle. Our army of, say, 50 servers that were running at peak are now mostly idle. Their CPU utilization drops to 5%. This is where the other side of elasticity becomes critical. Scaling in. Our auto-scaling policy has another rule. If the average CPU utilization of my violinist drops below 20% for more than 10 minutes, I have too many. Gently dismiss them one by one until the average utilization is back in a healthy range, but never go below our minimum of 4 violinists. The orchestrator sees the low CPU usage. It identifies a few servers, makes sure they finish any in-progress requests, and then gracefully removes them from the load balancer. Once they are no longer receiving traffic, it tells the cloud provider, "I'm done with these servers. You can terminate them." And instantly you stop paying for them. The orchestrator continues to do this until the fleet is right-sized for the current lower demand, perhaps shrinking all the way back down to just a handful of servers. This automatic, elastic dance of scaling up and scaling down is one of the most powerful and cost-saving features of cloud orchestration. You achieve a perfect balance. You never starve your application of resources during a peak, ensuring a great user experience, and you never waste money on idle resources during a lull, ensuring an efficient, lean operation. You are paying for exactly what you need, exactly when you need it. And the triggers can be far more sophisticated than just CPU. Imagine a video processing service. The trigger to scale might not be CPU, but the number of videos sitting in the to-be-processed queue. The rule could be, for every 100 videos in the queue, add 1 more processing server. As the queue grows, the army of workers grows with it. As the queue shrinks, the workers are sent home. This allows you to tie your infrastructure directly to your business logic, creating an incredibly responsive and efficient system. So, our orchestra can now grow to fill a stadium and shrink back to fill a small club, all on its own based on the size of the crowd. It's dynamic, resilient, and cost-effective. But this raises a new question. What happens when the composer wants to change the music, while the orchestra is in the middle of a sold-out performance? How do you update your application, roll out new features, or fix bugs on a live, scaling system without causing a single moment of downtime? How do you swap out the sheet music for every musician, potentially hundreds of them, without the audience ever hearing a single wrong note? The answer is, you do it with a level of planning and precision that would make a military strategist blush. You use a playbook. In the world of cloud computing, these playbooks are called deployment strategies, and they are the secret to changing the engine of a plane while it's in mid-flight. Our conductor, the orchestrator, doesn't just wildly hand out new sheet music. They have specific, battle-tested methods for introducing change. Let's start with the most common and intuitive approach. Imagine our conductor wants to introduce a new, slightly different version of the main theme. Instead of stopping the whole orchestra, they walk over to the first violin, take their old sheet music, and replace it with the new one. They listen intently. Is the first violin playing it correctly? Is it in harmony with everyone else? Yes, perfect. The conductor then moves to the second violin and does the same, then the third. One by one, musician by musician, the new music ripples through the orchestra. This is called a rolling update. In the tech world, instead of musicians, we have our containers, our little application instances. A rolling update works exactly the same way. The orchestrator, like Kubernetes, will take down one old container, let's call it version 1, and replace it with a brand new container running version 2. Then waits. It uses its health checks, our conductor's ear, to make sure this new container is healthy, running, and not crashing. Once it's confident version 2 is working, it moves to the next one. It terminates another version 1 container and replaces it with a version 2. This process continues, container by container, until the entire application has been rolled over to the new version. The beauty of this is that the application never goes down. At any given moment, you have a mix of old and new versions running, but the total number of musicians playing always stays the same, so the audience, your users, never experiences an outage. It's a safe, steady, and resource-efficient way to update. But it has a downside. For a period of time, you have 2 different versions of your application running simultaneously. This can sometimes cause weird, subtle bugs. And for a very large orchestra, this one-by-one process can be slow. What if you need a change that is dramatic, instantaneous, and perfectly synchronized? This brings us to a far more theatrical and frankly brilliant strategy. Imagine our conductor has a completely new piece of music. It's not just a small change, it's a whole new song. A rolling update would sound chaotic. So instead, the conductor employs a strategy known as blue-green deployment. Here's how it works. On stage, our main orchestra, let's call them the Blue Orchestra, is playing the current song for the audience. But backstage, hidden from view, an entire second orchestra, An exact replica of the first, with the same number of musicians and instruments, is warming up. This is the Green Orchestra, and they are practicing the new song. They run through it, tune their instruments, and get it absolutely perfect, all while the audience is just listening to the Blue Orchestra, completely unaware. The conductor can run all the tests they want on this Green Orchestra backstage. They can make sure every note is perfect. Once they are 100% confident that the new song is ready for prime time, they do something amazing. In the fraction of a second between songs, they give a single silent command. The Blue Orchestra is instantly whisked off stage, and the Green Orchestra is moved into its place. The downbeat comes and the audience hears the new song, played perfectly from the very first note. The change is instantaneous and flawless. This is exactly how blue-green deployment works in the cloud. You have your current, live production environment, the blue environment, serving all your users. Then you create an identical second environment, the green environment. You deploy your new application code to this green environment. It's completely separate and isolated from live traffic. Here you can run every test imaginable. You can have your quality assurance team hammer it, run automated integration tests, make sure everything is perfect. Your real users are still happily using the blue environment, totally oblivious. When you're ready, you flip a single switch at the router level. All incoming user traffic that was going to blue is now instantly redirected to green. And just like that, your new version is live. The best part? What if you discover a horrible bug a few minutes later? No problem. You just flip the switch back. All traffic goes back to the old stable blue environment, and you've had almost zero downtime. You can take the green environment offline to figure out what went wrong without any pressure. It's an incredibly safe, almost risk-free way to deploy. The only catch? It's expensive. You're literally paying for 2 full production environments, doubling your infrastructure costs for the duration of the deployment. So, we have the slow and steady rolling update and the expensive but instantaneous blue-green. But what if you're a company like Netflix or Google? What if your new feature is experimental? You're not sure if users will like it, or even if it will perform well under the crushing load of millions of people. You don't want to roll it out to everyone at once, even with a blue-green strategy. You need to test the waters. For this, the conductor uses their most subtle and clever technique, the canary deployment. The name comes from the old practice of canaries in a coal mine. If the air was bad, the canary would be affected first, warning the miners to get out. In our orchestra, the conductor has a radical new piece of music. They're not sure how the audience will react, so they don't give it to the whole orchestra. They give it to just one musician, the piccolo player. The rest of the orchestra continues playing the old familiar song. But for a small handful of people in the audience, those sitting right in the front row on the left, they can just faintly hear this new experimental melody from the piccolo mixed in. The conductor watches this small group of people intently. Are they smiling? Are they confused? Are they plugging their ears? They also listen to the piccolo player. Is he keeping up? Does the new music work? Based on this tiny sample size, the conductor gets real-world feedback. If the feedback is good, they might give the new sheet music to the entire flute section next. Now a larger portion of the audience can hear it. They continue to monitor. If all is still well, they expand it to the woodwinds, then the brass, slowly and carefully increasing the exposure of the new music until the entire orchestra is playing it. If at any point the feedback is bad, they just tell the piccolo player to go back to the old music. The blast radius of the failure is tiny. This is canary deployment in the cloud. You deploy your new code version 2, but you tell the router to send only 1% of your real live user traffic to it. The other 99% continues to go to the old stable version 1. You then watch your monitoring dashboards like a hawk. Are error rates for that 1% of users going up? Is latency spiking? Is user engagement dropping? You're testing your new code with real users in a real production environment, but the risk is contained to a tiny fraction of your user base. If the metrics look good, you dial it up. Send 10% of traffic to the new version, then 25%, then 50%, and finally 100%, at which point you can decommission the old version. This data-driven approach is the gold standard for large-scale systems. It allows you to test new ideas in the most realistic environment possible production, while minimizing risk. Rolling updates, blue-green canary deployments. These are the sophisticated techniques that allow modern software to evolve continuously without breaking. And the most important thing to remember is this: the conductor, our orchestrator, is the one making it all happen. You don't do this manually. You declare your intent. You tell Kubernetes, I want to do a canary deployment for this new version, starting with 5% of traffic and increasing by 10% every 15 minutes if error rates stay below 0.1%. The orchestrator then executes that complex, high-stakes ballet for you automatically. It's the brain that not only manages the state of the orchestra, but also manages the process of change itself. We've now seen how an orchestra is assembled, how it scales, how it heals itself, and how it can change its music on the fly without missing a beat. We've covered the core of what makes orchestration so powerful. But there is one final, mind-bending evolution of this concept. A place where the analogy almost breaks down because it's so advanced. What if the conductor's job could be fully automated? What if the sheet music itself contained all the instructions needed to assemble, run, and even update the orchestra, without a conductor even needing to be on the podium? That is precisely the world we live in right now. This isn't a futuristic dream. It's the revolutionary concept at the heart of modern orchestration, and it's called infrastructure as code. Think about that phrase for a second. Infrastructure as code. It means the very blueprint of your entire digital world. Every server, every database, every network, every firewall is not built by clicking buttons in a web browser or by a team of engineers manually plugging in cables. Instead, it's defined in a text file, a script. The sheet music itself has become intelligent. This intelligent sheet music is declarative. That's a key word. It doesn't tell you how to set up the orchestra step by step. It simply declares the final state. It says, the stage shall have 100 violins, 50 cellos, and 3 grand pianos, all perfectly tuned and ready to play Beethoven's Fifth. It doesn't care if a roadie starts with the pianos or the violins. It only cares that the end result perfectly matches the blueprint. You hand this file to the cloud provider, and the cloud provider's machinery reads it and builds that exact orchestra for you perfectly every single time. This is where the giants of orchestration come onto the stage. You've probably heard their names whispered in tech circles: Terraform, Ansible, and the undisputed king, Kubernetes. They aren't just tools. They are different philosophies for automating our digital symphony. Let's start with Terraform. Imagine Terraform as the master composer. The composer doesn't build the concert hall or tune the instruments. The composer writes the score. They create the master blueprint for the entire performance. Terraform does this for your cloud infrastructure. You write a Terraform file that says, I need 10 web servers of this size, a database of that capacity, and they need to be connected by this specific type of network. You hand this file to Terraform and it communicates with your cloud provider, be it Amazon Web Services, Google Cloud, or Microsoft Azure, and it builds that entire environment from scratch. It's the architect drawing the blueprints before a single brick is laid. If you want to change the concert hall, say add a balcony, you don't send in a construction crew. You just update the blueprint, you update the code, and Terraform intelligently figures out the most efficient way to add that balcony without tearing down the whole building. Want to build an identical concert hall in another city? You just use the same blueprint. Instant, perfect, repeatable infrastructure. Now what about Ansible? If Terraform is the architect who builds the concert hall, Ansible is the hyper-efficient stage manager. The hall is built, the chairs and music stands are in place, but now you need to configure each individual station. Ansible is the tool that goes to every single musician, one by one or all at once, and gives them their specific instructions. It can install software on 1,000 servers simultaneously. It can update security patches, configure files, and make sure every single component is in the correct state. While Terraform is great at provisioning, creating the stuff, Ansible is brilliant at configuration management, managing the stuff that's already there. It follows a playbook, a set of instructions. Go to all violinists and tell them to tune their A string. Then, go to all the cellists and hand them page 3 of the music. It's procedural, following a list of tasks to bring existing systems into a desired state. So Terraform builds the stage, Ansible sets up the instruments. But who runs the show? Who conducts the performance minute by minute, second by second? This is where Kubernetes comes in, and it's a game changer. Kubernetes is not just a conductor. It's a self-aware, automated, sentient concert hall. It takes the concept of orchestration to a level that is almost magical. In the world of Kubernetes, our applications, our musicians, are packaged into tiny, isolated boxes called containers. Think of each container as a musician who brings their own chair, their own sheet music, and their own perfectly tuned instrument. They are completely self-contained and can play anywhere. You don't tell Kubernetes, please put this musician on that specific chair. No, you treat your servers like a faceless, nameless pool of resources, a giant stage. You simply hand your containerized musicians to Kubernetes and say, I need 50 violinists running at all times. And Kubernetes handles the rest. It finds empty chairs and places the musicians. But this is where the magic begins. What if one of the violinists gets sick and stops playing? In the old world, an alarm would go off at 3 a.m. An engineer would wake up, log in, and try to fix the server. With Kubernetes, it doesn't even blink. It sees the musician has stopped playing, instantly vaporizes them, and creates a brand new, perfectly healthy clone to take their place. The music never stops. This is called self-healing. What if your song suddenly becomes a viral hit and the audience triples in size? The music starts to sound strained. The orchestra can't keep up. Kubernetes sees this happening in real time. It senses the load increasing and automatically adds more musicians to the stage. It scales your orchestra up from 50 violins to 500 seamlessly to meet the demand. When the crowd thins out later, it gracefully sends the extra musicians home to save resources. This is auto-scaling. Kubernetes manages the entire life cycle. It handles updates with zero downtime by slowly replacing the old musicians with new ones, one by one, ensuring the performance is never interrupted. It manages the networking, making sure all the musicians can talk to each other. It manages resources, ensuring the loud brass section doesn't drown out the quiet flute. It is the ultimate automated conductor, stage manager, and concert hall all rolled into one. It has become the operating system for the cloud. It's the invisible force behind a huge percentage of the apps and websites you use every single day. The reason your favorite streaming service doesn't crash during a new season premiere? That's orchestration, likely powered by Kubernetes. The reason you can order food, hail a ride, and get instant notifications from a dozen apps all at once? That is the power of a perfectly orchestrated, self-healing, auto-scaling digital symphony. This is why orchestration matters. It's not just about convenience for developers. It's about building systems that are resilient, scalable, and reliable on a level that was unimaginable just a decade ago. It replaces slow, error-prone manual work with fast, perfect automated systems. It allows a tiny startup with 3 engineers to deploy and manage an infrastructure as complex as a Fortune 500 company. It's the great equalizer. The entire journey we've taken, from a single physical server in a closet to the abstract idea of the cloud, has led us here. We learned to virtualize servers to be more efficient. We moved to the cloud to rent that efficiency on a global scale. We broke our big applications into microservices so they could be managed independently. And finally, we needed a conductor and orchestrator to manage the maddening complexity of thousands of tiny services all working together. We created a system so complex that no human could possibly manage it. So, we taught the system to manage itself. We wrote the intelligent sheet music, the infrastructure as code, and built the sentient concert hall Kubernetes to run the show. We've built a global digital orchestra that never sleeps, that heals itself, and that can scale to reach every person on the planet. And the most incredible part? The music is just getting started.